name is Amit, and I am a student of IIT Bombay from the Mechanical Engineering Department. I am currently in my fifth semester. We were studying integral calculus, and we will continue with our topic iterated integrals. So, what are iterated integrals? Basically, if any integral is being integrated with respect to two or more independent variables, then we'll have to integrate it one by one till we reach the outermost integral. So, basically, we have to integrate the function in a number of steps or iterations. So, for example, if we have an integral of this type, double integral x plus y dx dy, we can see that the inner integral is with respect to x and the outer integral is with respect to y. So in this, we will assume this to initially be a function of x and we'll take y as a constant. So integrating this with respect to x, we will get x squared by 2 plus y into x. And now for the second integral with respect to y, x is taken to be a constant. So we will get x square y by 2 plus x y square by 2. So normally for two variable double integrals, we can have two iterated integrals, first with respect to x and then with respect to y, or first with respect to y and then with respect to x. In general, these two integrals are not equal. However, there may be certain cases under which these integrals become equal, which brings us to the Fubini's theorem. So, the iterated integrals will be equal under the following conditions. F of xy is Riemann integrable over the given domain, and the integral of absolute value of f of xy over the domain should be finite. Under these conditions, we can switch the order of integration, that is x first or y first. So let us see this using an example. If we have an integral sine y by y dy, uh, first integral and second integral with respect to dx, in the range y between x and pi and x between 0 and pi. So we sketch the domain first to understand in which region we are evaluating this integral. So y equal to x gives us this straight line, while y equal to pi gives this horizontal line, and x between 0 and pi. So this is the region which is our domain, and we need to integrate this. So as we can see that this innermost integral sine y by y dy cannot be evaluated by normal means. So we need to think of something else here. So first we will see if this function is Riemann integrable or not. We can see that in this region, there is only one discontinuity for this function, that is a y equal to 0. So we had learned in the previous lecture that if the function is discontinuous at finitely many points, but continuous over the entire domain, then it is Riemann integrable. So here we had this function. So instead of integrating it with respect to y first, we can integrate it with respect to x because of the Fubini's theorem. So since you have to integrate it with respect to x, we will take strips of this form. So for x, we can see that the lower limit of x is x equal to 0, that is this vertical line, and the upper limit will be x equal to y for such strips. And in this domain, y goes from 0 to pi. So when we integrate this, it will come out to be y, and these two y will get cancelled. So we have a simple integral 0 to pi sine y dy, which can be evaluated to give the answer 2. Fubini's theorem fails in the following cases. If the function is double integrable, but one of the iterated integrals does not exist, that is, the integral is not finite, or both the iterated integrals exist, but f is not Riemann integral. For example, we can see this function here by following the rules of iterated integrals. If we evaluate this with respect to x first and later y, we will get the answer minus pi by 4. But if we invert the order of integration, we will get plus pi by 4. Since these two iterated integrals, uh, we can see that they exist, but they are not equal, even though the function is double integral. So, such kind of questions are quite important from an exam point of view. You just have to sketch the domain first and then check whether the integral is solvable by normal means or not. uh, you may be given functions such as sine, tan, or ln, which may give difficulty in solving the normal way. So, in such cases, we always look for Fubini's theorem and see if the function is Riemann integrable. If it is Riemann integrable, we can switch the order of integration to simplify it and get our result in a few lines. So, let us consider an important example. We have f of xy defined as this 1 minus 1 by q for x equal to p by q, that is x belongs to rational, and 1 otherwise, that is x belongs to irrational. So we need to prove that this function is integrable, but the iterated integrals may or may not exist. So we need to check that. So let us define this set S as 1 minus f of x comma y, uh, which is greater than epsilon, and take the domain as x and y belonging to 0 comma 1, because this is the only domain where we may get a possible discontinuity, and all other domains are basically replicas of this domain. We can see that S is a finite set uh, which consists of some L rational numbers, say, and all these rational numbers satisfy q less than equal to 1 by epsilon. We consider the partition P as we had done in Riemann integration for 2D, and we divide the x part of the interval into m subintervals and the y part of the interval into n subintervals. We can see that the difference between xj and xj minus 1, that is the subinterval x, is less than epsilon by L, because their each set consists of L rational numbers, and q is less than equal to 1 by epsilon. So here we will get the epsilon, and we divide it by L for each separate interval. And similarly, we get this difference between the subinterval y to be less than epsilon by L for all j belonging to 1 to n. The norm P in 2D case is defined as the maximum difference in any possible subinterval. So here, since these two are equal, we can say that norm P is less than epsilon by L. We had also defined m jk's as the infimum and supremum of the function, and the Riemann upper sum and lower sum is defined as the product of the respective m into the aij, which is the product of the subintervals at I and j. So here the difference between the upper sum and lower sum will be as follows, and we sum all these possible uh, rectangles. Uh, First, we will split the sum into two parts, such that one of the parts contains at least one point with x belonging to this set S, which we have defined here. In the first part, we can see that this difference is greater than equal to 1 by q, because uh, this is the maximum part of this function and this is the minimum. So maximum should be 1 and minimum should be 1 minus 1 by q, where q is a natural number. So the maximum difference will be 1 by q, and we have defined q less than equal to 1 by epsilon. So this difference will reduce to epsilon, and this sum is then reduced to 2L into epsilon by L, which gives 2 epsilon. In the second part, we have seen that this reduces to 2 epsilon and the first part reduces to epsilon. So the total difference of the upper sum minus lower sum is less than equal to 3 epsilon. We can take this as some epsilon dash. And since this epsilon dash tends to 0, we can see that upper sum and lower sum converge. So this proves that the function is Riemann integrable. So iterated integrals may exist, and we can integrate the function to find the if both the iterated integrals give the same value. So in the first case, we take the iterated integral with respect to x first and then with respect to y. So we define some phi, y, and x, which is equal to f of xy for fixed y, because since we are integrating with x first, the y part will be fixed. Here we just apply this definition to that given in the question, and we will see that this function attains the value 1 minus 1 by q at x equal to p by q, 1 otherwise, and 1 if y belongs to irrational. We can see that these two upper parts are actually definition of the Thome function, which we had learned in the previous class, and this part can be written as it is. So this upper part basically reduces to 1 minus Thome function for all y belonging to rational. We have learned that the integral of the Thome function over any interval is 0. So this integral phi y will be 1 for both this and this. So the iterated integral exists and its value is 1. In the second case, we will integrate the function with respect to y first and then with respect to x. We define a function phi x of y equal to fxy for fixed x. Now we can apply this definition and see that from the question that this will have three parts: 1 minus kx, where k is basically a constant, where x was defined to be p by q, and this part was given as 1 minus 1 by q in the question. So we need to define some constant k equal to 1 by p. So basically this, we need to show that this part just depends on x because k is a constant over here. A 1 otherwise as given in the question, and 1 if y belongs to irrational. Using the first two parts, we can see that this is nothing but the 1 minus Dirichlet function, which we had studied in the previous lecture, for all y belonging to rational, and 1 if y belongs to irrational. Since Dirichlet function over any interval is not Riemann integrable, which we had learned, even though it looks similar to the Thome function, it is not Riemann integrable. And because of this property, we know that the iterated integral will not exist. So you can solve similar questions of Riemann integration and Darboux integration using these properties that we have learned. So thank you for watching this lecture. You can scan this QR code to know more about us.